Well, welcome back everyone so far. Looks like we've got just about a minute to go. By the way, the computer was running really bad last time, and I think I found out the issue. I looked over here under this little doohickey, and the uptime was something like 40 days or so. So it was just, most computers are just fine with that, but I think they had a lot of updates on top of all that, and it just been left on forever. Or maybe there's updates pending, and it couldn't actually install them with the runtime being so long. Who knows? Well, week three is official. Welcome back, everyone. We're kind of just running through them pretty fast. At some point in the semester, it feels like it's going super fast. Other times, it feels like it goes slow. This might feel like a more slow week because it's a pivotal one, right? We're getting to our very first exam week. So it's going to be next Tuesday. I got this information posted kind of late in the weekend, and I also had your homework graded pretty late in the weekend as well. So full disclosure, I did catch a cold. I'm getting over it, so I don't think I'm in the infectious stage right now for the people here in person. And here on Zoom, you're definitely safe. But as far as the exam one content is going to go, it's going to be from sections 1.1 through 1.4. So that's going to involve the last section here that we're about to finish today. So really, there's three best ways to kind of prepare for this exam. The utmost biggest thing you could do to prepare for it is being caught up on these homework assignments 1.1 through 1.4. Even if you got to 1.1 late, just about everyone's turned this one in. But if you miss this one and you're just sitting on it, I'd say go ahead and complete it, turn it in. I will still accept it for full credit. Sooner you can work on 1.2, 1.3, the sooner I can get these graded and returned to you. And I should be not sick at all by the time Friday comes around. And I'm going to make it my goal to just work through the homework as soon as possible. So that way you have great feedback on these sections, 1.1 through 1.4, to help you prepare for the exam. In fact, even though this one has a due date of the 16th, the same day of the exam, if you do hand this in to me early, say on as late as Sunday, I'm going to still make an effort to get that graded and sent back to you. Well, other questions about the exam so far? Okay. Well, I have a few extra documents you'd want to take a look at. Each one of our exams is going to have something like this at the very back. I just generically call it a formula sheet. Sometimes it's theorems, sometimes it's definitions, sometimes a little bit of both. But these are the things that are going to be at the very end of the exam. Not too much, but I felt like theorem four does have a lot of interesting facts, logical equivalences. So I put this one on the back of exam number one. And I don't know if I remember leaving the highlight on there. I think I took the highlighting off. At theorem two, well, this didn't really have to be there. We get to the point where we take it for granted. But just so it feels like there's not just one small thing, I threw in theorem two as well. So these are the things that you can take for granted on the real exam as a provided two theorems. The rest of the content is up for us to retain and have memorized for the purpose of the exam. Oh, and before I forget, I had one other big announcement. When I graded section 1.1, I thought folks in this class did a really great job doing their work, showing the row reduction steps and that kind of thing. But I did run into some kind of weird issues. I did make out a big announcement that you might have seen that if you're working at an older edition, then you ought to click on the assignment itself to look into the PDF so that you know you're solving the right exact problems. So looks like this. Click on the assignment. I think you have to anyways to reveal it. Then this is out of the current edition, the 1.4 PDF. I also realized it's not fair to have like the fifth edition because you saved a whole bunch of money, but you know what the answers are, not the back of the book odd solutions. So I posted this as well. So everyone's kind of on the same playing field in a certain sense. These are the odd solutions. Some of them are pictures right out of the textbook. Other ones I just typed them out as verbatim as possible, slightly different size brackets, but the same verbatim solutions. So that way you'll know the exact problems are working and their solutions. In section 1.1, it didn't cause too much trouble because you're doing kind of the same problems with different numbers. But in either sections, you might be doing a computational problem or excuse me, you might be doing some kind of long proof problem when you're meant to be doing some other computational problem. So it could cause some big issues down the line. And another student reminded me, well, didn't remind me, alerted me to something I didn't even know. Some people may have been, excuse me, talking's hard. I'm going to blame this on the cold. Some people might have purchased the 6th edition, but it's in fact a global international edition. So there is an ISBN on the syllabus if you want to know the exact edition. I should have mentioned this on the first day of class, but there's a million things we talked about on the very first day, it feels like. This is the actual edition right here, but then there's a so-called global or international edition of that one, which is cheaper, so you might save some money on that. Good on you. It's still going to work great for the class. But even that, sadly, 6th edition global version or international version, whichever it's called, does have different homework exercises. So that kind of stinks in a way. Sorry about that. I should have been more clear. But still, if you do have a different edition, just keep on clicking on these assignments. Oh, that's the blank lecture notes. I'm always going to post the exact answers so you know what problems are you really doing to match up with the course and the back of the book auth solution, so that's more of a fairness issue there, that we're not just kind of left out if you save some money on the book. But I think that's my full set of announcements. Unless I forgot something, then maybe we'll come back to it next class. Any questions or comments at the moment? Okay, and I can tell my thoughts are a little bit jumbled here, so sorry about that if I'm kind of going backwards and forwards on stuff. Other things I want to point out in the exam is best way to prepare is to get through the homework, take a look at the feedback. When you're studying for the exam, you might want to be aware of this formula sheet right here, just to have it up so that you know it's something that's going to be provided. And these are just additional problems that you could take a look at. Version 1, I'm going to do this for all the exams, including the final. Version 1 looks like this. It's really just the actual lecture notes that we've been working through with all the formulas, definitions, and material taken out. Now it's just a worksheet. This is what it looks like as actual exam questions. Problems that didn't work out as good exam questions are just taken out. So that's why an example could be skipped, like there's no example 1 here. These are kind of rehashed problems, but they're still really valuable questions because they'll prepare you for what real exam problems are going to look like. Same style of questions, same kind of formatting. If you want even more practice, version 2 is just a whole bunch more problems that are kind of homegrown type, homebrew problems I made up. This one has the solutions at the very back of the page. So on the very bottom here is solutions. Typos do happen, so if you see anything that seems odd, don't hesitate to reach out and I'll get it corrected right away. Okay, I think I went through all the announcements. It took me 8 minutes. That's a good amount of time. But any last questions at all, folks, before we jump back in to example 2 here? Okay, well, in section 1.4, really it's kind of a rehash of what we've been doing so far in section 1.1, 1.2, 1.3. Only difference is now we're looking at systems of linear equations presented now as a matrix equation. Because we're looking into the matrix equation, the first thing we're really studying is matrix times a vector style multiplication. Our first definition we looked at was, what does A times a vector X really look like? First, there's a check to determine if the product is defined. The number of columns in the matrix, that's the purple, the 3 here circled in purple, must match the number of entries, or often we say rows, in the vector. If that's defined, all we did was take each one of these entries here, switch out the color coding, form this specific linear combination, and just do scalar multiplications, vector additions to get down to that product. So the textbook, when you do this as a homework problem, is going to ask you to do it 2 different ways. By the definition of AX, that's what we mean right here. So this was method 1. Definition, if I can spell that right, let me try again, of AX. It's really just a linear combination using these particular scalars highlighted in blue. And the author shows another way, which is important because if we have to do this every single time we do a matrix times a vector, it just turns out takes too long. When we do a matrix times a matrix, this could take pages of scratch paper to get through. And so this is version 2, the row vector rule of computing AX. Method 2, row vector rule. And this is the version that we do in practice. So we must master this method. Think of method 1, and a more abstract way to look at it, which is helpful if we didn't actually know this was a -4. Maybe it's a x1, x2, x3, and we're just considering this linear combination here. Method 2 is used more often than not if you do know those numbers and you're just trying to get the resulting vector. So it's the same exact matrix A, same exact vector X. This time what we do is we focus on the entire first row, 1, -3, 0. We multiply by the corresponding entries, -4, 1, 2, and add up the entries. And I vaguely remember at Thursday's class running through this and getting mixed up on my arithmetic. So let's see if the cold medicine is helping out this time. Take 1 times -4 for a -4, -3 times -1. We're adding these together, so we're up to -7 plus 0. So first entry is -7. And now all we do is same exact song and dance, but it's row 2 now. For people who have taken Calculus 3, I seem to say this a lot at the start of class, or if you are taking it, really we're just taking a dot product of this row against that vector and putting in the entry. Dot product means multiply corresponding entries and add them up. So now it's -3 times -4 up to +12, 4 times 1, so 12 minus 4, we're at 8, plus 2 times 2, plus 4. 8 plus 4 will take us up to 12. Last, the focus goes down to this row. It's 1 by -4, so -4, plus 6, so we're at a balance of 2, plus 2, so now we're at a balance of 4. And I keep forgetting the highlighters there. So we get to the same exact result. Let me just fix my penmanship on that bracket. -7, 12, 4. So method 2 is extremely fast, not a lot of scratch that we won't work out. And method 1 is just the core definition of what we're doing. But as you look at this, really we're saying the same thing, right? Because if you take these entries, multiply these corresponding entries, add them up, you're doing the same thing either way you're visualizing it. Well, that's our first part here on example 2, part A. We're going to take a look at a couple more just for practice. But any questions or comments, folks, running through those multiplications? Okay, again, homework says do it both ways for practice. If you decide to do that, no harm done, but you're welcome to focus on this if you prefer. I'll leave that to be totally up to you. A lot of people just follow the instructions to the letter, but oftentimes that could lead to a lot of unnecessary work in some cases. This is one of those cases. Let's try it out. This time we're taking the matrix down below here. This one we called a 3 by 3 matrix to mean 3 rows, 3 columns. What would you all call this one? Is this 3 by 2 or 2 by 3? Good call. From class, this is a 3 by 2 matrix. And that's suddenly the most important observation to make of all, right? Because the vector over here is 3 by 1, 3 rows, 1 column. And that means this problem is an automatic freebie. There are 2 rows, or excuse me, 2 columns there and 3 rows here. This means the product is undefined. That's all we have to say, just undefined. If you're asked to explain why, you could just verbally write out there are too few columns to correspond to the 3 rows. That would do it. There's not the same exact number of columns as there is rows. Or you could just write out dimensions like we did, emphasize where the problem is, and that's a fine way to answer it. So I would consider this to be a perfectly good explanation. If you're more person who likes to write out in words, you might say undefined. Because A, well, that's kind of out of nowhere, right? We didn't define A, but A is taken to be the matrix. So if we read the context on this one, you're probably referring to that matrix A there, because A has only 2 rows, and X, well, again, I didn't define what X was on paper, but reading through the context clues, we're probably referring to the vector. And X has, oh, let me fix that. It has only 2 columns. Let's emphasize that. And X has 3 rows. So either way you say it, we have undefined here, and that just means we can move on to the next one immediately. Imagine if you did try to actually work it out. Either way you did it, if you went this route, the vector here in this position would be missing because there's only 2 vectors appearing here, yet 3 scalars that has to be brought in here and here and here. So visually we know something is just wrong by looking at it. But there's really good value in writing this out because this one looks kind of funny too. If you imagine this vector as, say, like a moving over towards where it's sideways, it has the same number of entries, you're defined. So that's one way to visually tell we're okay. Also, you could just think in terms of these dimensions. The matrix A here has 2 rows by 4 columns, so a 2 by 4 matrix. Vector here has 4 rows, or 4 entries if you prefer to say, by just 1 column. So it's 4 and 4 here for a match. This is a defined product. Let's say product, although you don't have to say this, the more for the notes. The product is defined. That means we can work this out. And one thing we might want to know is, well, how big is the product itself? Turns out these dimensions are giving you really the full story. They're telling you when you can multiply, when you cannot. You're just looking at the inner dimensions where we've been boxing them or circling them. The outer dimensions, the ones in green here, these are going to tell you the size of the resulting product. It's going to be 2 by 1. So that's kind of nice in a way. You'll know just how big of a container to put your result in. And then it's just multiplication as before. We're going to pair up all the scalars in the vector, first with row 1, multiply them together, add up the result. So here to here, we'll have 6 plus 0, minus 3, so we're at a balance of 3, minus 18, so we're at 15 on the first entry. Let me know if my arithmetic goes sideways on these. It just feels like a lot more to keep track of with 4 entries. Then do it all over again, more arithmetic. I think we made this comment already. Linear algebra is one of those classes where I felt like I got really good at arithmetic because there's just so much of it to do. This kind of arithmetic, nothing fancy or anything. But 3 by 6 gives us 18. Minus 4 takes us down to 14. Minus 2, we're at 12. Then minus 3, that's going to take us to 9. Look, I might have made a mistake on that one. Does that look all right to folks? Let me double check both of them. So for first, I'll have 6 plus 0 minus 3. So I'm going to balance at 3 minus 18. So I'm going to be at a balance of negative 12. Really messed that one up. Negative 15. Yes. Let me try again. I believe you all. I'm just going to blame the cold again on this one. 6 plus 0 still has 6. Minus 3 at a positive 3. Minus 18 is a negative 15. Yeah, thanks for the help on that one, folks. Now the 9 is suspicious to me. Let me try that one again. 3 by 6 is 18. Minus 4, so I'm at a 14. Minus 2, so I'm at a 12. Minus 3, so I'm at a 9 altogether. Does that would seem all right to folks? Okay, the one I was most suspicious about was correct. I was confident on that one, but that one turned out incorrect. Let's imagine that was a real exam question. This is stuff we're going to do on our first exam. What I'm going to really be looking at is, well, how well do you know the concept? I can tell you're doing everything right, but maybe you missed a sign or something like that. Out of a 5-point problem, you might just lose a single point. Not too big of a deal. If you do a row reduction and maybe you made a mistake at the very first step, I'm going to have to very carefully track all the rest of your steps. But if it was just that one mistake, again, you might just lose 1 point out of 5. It's if I totally mess up and say, try to put a number down on this one when it's undefined, that's when I could lose all the credit on a particular problem. Well, we did it, folks. That's matrices times a vector. This leads into new things that we want to talk about, different ways to express systems of equations. But any questions at the moment with these arithmetic type properties? Okay, on to our next things is the so-called matrix equation. And this is kind of interesting because now we have 3 different ways to write out the same thing, a system of linear equations. We could just write out a system. We could write out the system of equations as a vector equation, or we could have the so-called matrix equation. AX equals B is what we would refer to as such a matrix equation. So in other words, this right here is now a matrix times a vector equals a vector. This would be a matrix equation itself. However, we just knew what was here. This is typically where the unknown would be. So 3 ways to express something. And what makes this also sometimes a tricky topic, especially if this is asked as a type of exam question, keep in mind that the augmented matrix is a separate concept. A very useful one. I mean, we've been using it since section 1.1 to solve the systems, but the augmented matrix is not the same as the system of equations. It's not the same as the vector equation, and it's not the same as the matrix equation. So just watch out for that. The instructions can sometimes be vague on exams. If you're ever asked to write out a matrix equation, it's got to be that. It wouldn't be the augmented matrix. That's a whole different concept. So if we have a matrix equation, this is going to be playing the role of A, this whole thing right here. The right-hand side is B, and for lack of colors, put X in yellow. So that's the unknown for AX equals B. We want to write this as a vector equation. Really, we now have to use the core definition of a matrix times a vector. It would just come together as X1. Let me fix my colors first. X1 multiplying 1, 1, negative 3 plus X2 multiplying 3, 5, negative 7 plus X3 multiplying negative 4, 2, 6. And it's all now equals to the right-hand side, the vector B in the definition above, negative 2, 4, 12. So same exact solution set, either if you're here as the vector equation or up here as the matrix equation. This is just one new way to totally visualize the same exact information. And this is something we did in section 1.3. Whether it's the vector equation or the matrix equation, we want this system of linear equations. We just write things out entirely. So imagine expanding all this, equating both sides of the vector equation, and you would get that x1 plus 3x2 minus 4x3 equals negative 2. So all I'm doing is multiplying across row ones, doing the scalar multiplications, vector additions, equating to -2. And this would just be the first entries of the left vector and the right-hand vector, -2, 4, 12. Then let's just do it over again for completion, focusing on row two. All I'm doing is grabbing those entries in the constant vectors. So 1 times x1 for x1, plus 5x2, plus 2x3, equals 4. Lastly, -3x1, minus 7x2, plus 6x3, equals 12. This is not my best penmanship. That's a 3 there if you were wondering. That's kind of a lot of color coding, but just for extra emphasis, the scalars that are shown, that's where they came from. Just assume those are ones that I decide not to highlight, to leave in simplified form. So now, 4 different ways to look at information, right? The augmented matrix, system of equations, the vector equation, and the matrix equation. It's good to pause here and just discuss what each one of these things are good for. We know that the augmented matrix right here, this is really just a by-hand computational technique. We use that either to determine if the system is consistent or not, or we're going to use it to totally solve the system when necessary. What's the value of the linear equations? Well, if you're working in something applied, if you're setting up the system of equations, this is where you would start. So maybe it's something in physics, balancing forces on a bridge. Maybe it's balancing a chemical equation, something from electrical and engineering. And you're first analyzing a system, you're writing down these equations line by line. So here, you're just building something that you're seeing in a physical system. If you're dealing with the vector equation, we'll see the purpose of this, or the value of this, is now we're analyzing the columns here, here, and here to see what properties might they have. Linear independence and linear dependence are things we're going to start breaking into in section 1.5. And if you're looking into the matrix equation, the big value here is you're analyzing the properties of the matrix itself as it relates to the system of equations. And already in these notes, that's what this theorem 4 is all about. Analyzing the underlying matrix that sits under your ordinary system of equations, no matter where they came from. Just a made-up math example on paper, or maybe something more real, like balancing a chemical equation, for example. So each one of these has its own purposes. In some parts of linear algebra, you can only write down the vector equation. There is no matrix equation. That depends on the vector space. And so it's really important just to be fluent with all 4 different representations. Again, augmented matrix seems to take second stage here. It is important, but this is really just our computational technique. But any questions at all, folks, on taking a look at all these different ways to represent the information? Okay, well, as the notes suggest, this is the major thing we want to study here, the matrix equation, and particular properties of the matrix itself right here. So we're getting onto some of these interesting theorems, and here it is, theorem 4. It's a really tricky theorem, so we want to spend some time with this one. It says, let A be an M by N matrix. So that tells us that's the number of rows. N is the number of columns. This is a really critically important matrix because even though later on in chapter 2, we have something called the invertible matrix theorem that we looked at just briefly to see what's going on in this course, that invertible matrix theorem is only applicable if the number of rows equals the number of columns. So this is the more general theorem, even though it only has 4 parts, because it works for any size matrix whatsoever. Here's another thing to be really, really careful about when you read this theorem. A is not an augmented matrix. This causes all sorts of trouble because a lot of us are just ready to go with this fact right here from section 1.2. Sorry for the sudden thing here. Oh, geez. We have a new PDF reader program that was just installed. A lot of people are really ready to go with, hang on, I don't know where my Zoom controls are. Ready to go with this theorem. But theorem two, the existence unique to this theorem, is talking about an augmented matrix where B is the part that has been augmented. So this theorem talking about an augmented matrix tells us something about consistency and inconsistency. This one is not an augmented matrix whatsoever. So having a column on the far right isn't going to tell you anything about consistency or not. So we have to be really careful with this theorem. In other words, like we were hinting at above here, we're only looking at the matrix part, not the right-hand side you would have augmented into with the augmented matrix on this concept below. So this is the statement of the whole theorem. It tells us the following statements are logically equivalent. We hinted at this before, but let's restate what we mean here. This part means all statements simultaneously true or simultaneously false. Kind of rough to say simultaneously twice. That's a lot of words. But just to emphasize, I think that's important emphasis there. So for example, if I grab a random matrix, like say this one, and I just happen to know the columns of A span Rm, then I would also know it has to have a pivot in every row. Every vector B in Rm is a linear combination of the columns of A. For every B in Rm, Ax equals B has a solution. So the system is always consistent right here. All those statements would be true. Or if I happen to find that this part's false, all the parts above are false at the same exact time. So they're all true together or they're all false together all at once. Some of these statements are remarkable. Notice when it says for each. We're talking every single vector you come up with. No vector is left out here whatsoever. Ax equals B has a solution. So this is about being consistent. System is always consistent. Doesn't matter what you change the right-hand side to, we can find a solution, it tells us. That's a really, really big statement. It turns out that statement in here, part A, is logically the same exact thing as saying, well, for every vector in B, it's a linear combination of the columns of A. So this is about linear combinations. Guess that's kind of redundant. It literally says linear combinations. But the reason that's true is if you take the matrix equation Ax equals B, you just write a linear combination of the columns of the matrix A, and we're looking at the same system. So part B is just saying the matrix equation is the same as the vector equation. Here we're just emphasizing the linear combination by writing a vector equation. Next, this is a bigger, deeper statement. The span of the columns of A is the set of every linear combination you could get from the columns of A. So this is a big statement on spanning. Turns out, always being consistent means if you span the columns of A, you get every single vector point in your target space. So this one has 3 rows. If there's a pivot in every column of this matrix, then the span of all 3 of these columns will be the entire space R3, in other words. So 3 big statements. There's a T there. And the amazing thing in linear algebra is, even though some of these statements are pretty big and deep, like the spanning one feels like it's saying a lot, they're all logically equivalent. They're all saying the same thing. And there's one huge tie-in. This is where you get your foothold. If you know the pivots of that matrix A, you know everything. If there's a pivot position critically in every row, that deserves some big emphasis. So this is all about the rows. And if there happens to be a pivot in every single row of that matrix, everything above is true. These things above are hard to check algebraically, but not part D. That's what we've been practicing all along throughout the course. So if you know the pivots, you know all this additional information in parts A, B, and C. So that's the rundown of this theorem. The next part of the notes is just practicing different ways to apply it and seeing what this theorem is telling us. Any questions or comments about it so far? Okay, just to practice now with this theorem, here's a random matrix A. It says nothing about a system of equations in the background here. It's not an augmented matrix whatsoever. If a matrix is augmented, I have to always say it on paper so that's very clear, especially because of theorems like this. If you have an augmented matrix, theorem 2 is now on the table and says really important things as well. So the question on this one is, if A1 denotes this column, 1, 1, negative 3, A2 denotes the column 3, 5, negative 7, and A3 denotes the column negative 4, 2, 6, we want to know if B, some other vector, is in the span of A1, A2, A3. But what we cannot do is pick a vector B. I can't just pick 1, 1, 3 or negative 5, negative 7, negative 8, for example, for my vector B in R3, because the question is about every single one, and I can't exhaustively check every single vector B whatsoever. What you could do, and the book actually does this as an example you might have read, is take this matrix, augment it with B1, B2, B3, where we don't say what those values are and just do a whole bunch of algebra. The reason the author did that problem was to show you the amazing power of Theorem 4. That's not the best way to work this problem. Theorem 4 says, take this whole question as B in the span of A1, A2, A3, for every B in R3, and see which part of Theorem 4 it relates to. It's not really about consistency or linear combinations, but it is about spanning, right? The columns of A spanning Rm is the same statement as saying every vector B in R3 is the result of the span of A1, A2, A3. So B is inside that span is the same thing as saying the columns of A span all of Rm, R3 in this case. So let's give this a try. We're going to use part C. And part D of theorem 4. And all we have to do to make that happen is just take A equals 1, 1, negative 3, 3, 5, negative 7, negative 4, 2, 6, and row reduce it. All we need on this one is echelon form because we're checking if it has a pivot in every row. If it does, we'll say yes, pick any vector B, and it's inside the span of those columns of the matrix A. And if it doesn't have a pivot in every row, we'll just say no. It's B is not in the span of A1, A2, A3 for every column vector B that we can think of. There are some exceptions. So let's run through the row reduction. We have 1, 3, negative 4. Let me fix my penmanship here first. First thing I want to do is eliminate that entry by the red dot. So multiply row 1 by negative 1, add below to get 0, 2, 6. To eliminate the negative 3, triple row 1 and add below. So we'll get 0, 9 minus 7 for a 2, negative 12 plus 6 for a negative 6. And it's working out pretty well. We now have pivots in column 1, column 2. Looks like we'll get a pivot in column 3, but we need to show that row reduction step for the sake of showing all steps on this kind of process. So 1, 3, negative 4, 0, 2, 6. Now multiplying row 2 by negative 1, add to row 3, gives us 0, 0. Multiplying by negative 1, so negative 6 minus 6 for negative 12. So we have a pivot going here, here, and here. That means there is a pivot in every row, it turns out. And so that means we can answer this part right here. Easiest thing to miss on this is not stating the full conclusion. So here I would say there is a pivot in every row. Definitely think row here. sure, if there's a pivot in every row, there's also a pivot in every column because there's 3 rows and 3 columns. It's a square matrix. But if it was non-square, maybe there was 4 columns. It's important to think this theorem is only talking about rows, not the columns. There's a pivot in a row. So yes, B is in span A1, A2, A3, or all B in R3. My conclusion's kind of clunky. You might have said it differently. You might have said, alternatively, yes, B is in, or let me say this differently. That's going to be the same statement. Yes, span A1, A2, A3, equals R3. That's a superscript. There we go. If you said it this way, you're saying the same exact information. This is a lot more compact. And this is just a long way of saying the same thing. Yeah.
Could you just say the span of A?
I would say that's okay, but there's kind of an interesting problem that does occur because we're going to get into vector spaces that look like this. Are, say, 3 by 3 is a set of all matrix A such that A has 3 columns with 3 entries, all in R. And this alone turns into a vector space in its own right. It's going to be a 9-dimensional vector space, and span A has a different meaning than span of the columns of A. That's really kind of annoying in a certain sense. But another really nice shortcut that you could use here is you could say call A equals R3. This one's another preview. We're going to have things called null space, row space, column space. If you write call A equals A, you're essentially saying the span of A, but you mean A's column specifically, is R3 itself. Whereas span A, again, this are really tiny issues, but it really has a whole different kind of meaning itself. It'd be reflecting all multiples of that matrix A in the R3 by 3 vector space. But does that make sense with that question there? Awesome. These are the weird little things that come into linear algebra. It's no different from calculus, where it has its own really precise notation and changes a little bit of elements from one to the other, and you might have a totally different meaning. Just like dy dx and dx dy are wildly different concepts, even though it looks the same on paper almost. Well, other questions at the moment? Okay, so this is probably what the author is thinking of as an answer. These are other things you could have said that are totally fine as well. Example 5 feels like it's out of place, and it's kind of intentional just to compare what we did in here, part A. We used theorem 4 directly because it was about an unknown vector B. We were talking about for every B in R3, so it was arbitrary. We want to know if it would be in the span of the columns of A. And example 5 feels like a very similar question, except the vector B is now a vector U, and we know its value. 4, -1, 4 is the one we're checking specifically. So there's the vector U. A is this matrix here. And we wonder, is U in the subset of R3 that is spanned by the columns of A, why or why not? This one's kind of a different sort of question. You might have used theorem 4, and if there is a pivot in every single row, then you'd say, yes, it didn't even matter what vector this was, it's going to automatically be in the span of the columns of A. But that's a dangerous step, because if you row reduce this, and there is not a pivot in every row, then you don't know the answer to this question. It could still be in the span of columns of A, or it might not be. So this one's a whole different question to compare how theorems are sometimes fantastic, and other times just not as useful. This is the not as useful scenario. Let's rewrite this whole question. Is U in the subset of R3 that is spanned by the columns of A? In other words, it's asking is U in span A1, A2, A3, where this would be A1, this would be A2, column 2, this would be A3, column 3 of the matrix A, and this is the same as asking is AX equals U consistent? So we can just change the whole question around to this statement. We have the matrix A provided. It's this stuff right here. X is the unknown, but we have the vector U playing the role of the vector B in the prior question. So really just a matrix equation type of problem. We're not going to use theorem 4 because we have a specific matrix to use, and this is the more straightforward way to go. And the very first thing we do is just immediately convert this into the augmented matrix. In the augmented matrix, we will have 2, 0, 1, 5, 1, 2, -1, -1, 0, augmented with 4, -1, 4. And this is all we need to work out. We're determining if it's consistent or not. We're not trying to fully solve the system. So we're just going to go for an echelon form on this one. By the way, it's kind of annoying, right? You could work with that 2 and make this happen. You could divide by 2 into that row. But smarter way to go, I'd say, is just interchange rows 1 and 3. A lot less arithmetic. It's a good idea to try to avoid fractions at all costs because they're terrible in the sense that they can increase your workload on this one. A lot of mathematics is just trying to figure out the way to do the least amount of work so we have the highest amount of accuracy. And this is a better start, I would say. We can pivot off of this entry here. So let me copy in both rows 1 and 2. 1, 2, 0, 4, 0, 1, -1, -1. Now multiply row 1 by -2, add to the row 3. It's going to give us -2 plus 2 for a 0, -4 plus 5 for a 1. No change. You have to love the zeros there. -8 plus 4 for a -4. Now we have pivots, columns 1, column 2, and all we need to do is add entries together. Row reduce further, and we get down to, let me copy in rows 1 and 2 again. 1, 2, 0, 4. Sensing this is the last step, so I'll put in the dash line. 0, 1, -1, -1. Now multiply, I'll put in that 0 there, that can't change. Multiply by -1 into row 2. Add to row 3 will give us -1 plus 1 for a 0. +1 minus 1 for a 0. +1 minus 4 for a -3. And lo and behold, if you're looking at this part, if you only row reduced this matrix, it does not have a pivot in every row. That means every vector U in R3 is not in the span of these columns. But because we augmented, we were working in a section 1.2, 1.3 kind of setup. Augmenting told us something even further. We have a pivot here in the rightmost column. And only because this one's an augmented matrix, now this theorem is on the table finally. We were working with the augmented matrix from the beginning. we found a pivot in the rightmost column, and so we can say it's inconsistent. What's inconsistent? The matrix equation way up here, which tells us, moving back a step, U is not in the span. So here's how I'd probably tie this up. Let's put a dot there. It's like one big sentence. The system is inconsistent. You don't always have to say at this point inconsistent because there's a pivot in the rightmost column of the augmented matrix. We'll take that for granted. That's the major concept that we've been working on for most of the course already. So if you just said inconsistent and I see this on paper, then that's enough explanation already. Because it's inconsistent, we can now say, and so U is not in either right span A1, A2, A3, or you could write call A. It would mean the same exact thing. We just haven't formally defined it yet. U is not in span A1, A2, A3, referring to those original column vectors up here. So kind of a throwback equation. We've done a very similar problem in the prior notes in 1.3. But it's good to redo this one just in the view of theorem 4 on the table to see when it's maybe less useful. It really wouldn't have helped us out at all in this kind of problem. Well, any questions, folks? Finalizing this one here. Okay, and just for the sake of emphasis one more time, if the coefficients here were different, and there was a pivot right here, a pivot in every row, you would not have had to augment. You could have just automatically said, yeah, it didn't even matter what the constant vector was. It's automatically inside the span. And it could have been potentially consistent if that was a 0 right there and still had not a pivot in that position. So really anything can happen in this kind of problem. This is probably just the safer way to do it so that you don't end up row reducing twice in this specific situation. Well, these notes are just about done. What's left over is just another look at theorem 4, just to get the extra practice. And also some more notational matters. I've mentioned a lot already in this course that we often write our column vectors as literal vertical columns. It reveals the structure of the matrix algebra. Matrices times vectors is what we've done already. The matrix times a matrix we build onto from what we've already done. And yet the book sometimes does this. Sometimes our author in his own printed text is going to write his column vectors sideways. What possesses him to do that? He's saving on paper. That is literally the only reason. It just turns out to be costly to print out column vectors on every single exercises, and he wanted a shorter book. So that's not a bad thing to do. It's just something you have to get useful because it looks weird every now and then. So V1, V2, V3 are defined in this way. And the question is, does V1, V2, V3 span R4? That's an interesting question. It's a spanning question, so that indicates we're probably using part D right here. If we're using part D, well, the way to get to it is looking into the pivots. We're almost always looking into part E for this kind of theorem. But it's talking about the columns of A, and no matrix A has been defined. That's okay. It's up to you if you want a new algebraic structure. You can just start by saying let A equal V1, V2, V3. Let's actually write it out. It's kind of hard to see what's going unless you have a really good visual imagination. You can really visualize this nicely. But for me, I'd have to really just write it down. I'll go 1, 0, negative 1, 0 for V1. When I put V2 here, no, not comma separated this time. I'm just saying that's the second column vector of the matrix A. So write in that V2. 0, negative 1, 0, 1. Third column vector goes 1, 0, 0, negative 1. And what some people might do right at this stage is begin row reduction. But do we have to? Anyone see something special about this particular matrix? The row reduction is not bad, right? Because row reduction will reveal the pivots. But anyone see something you could say about the pivots? What's the most you could have? Exactly. The most pivots you could potentially have is 3. Maybe there's 1 or maybe there's 2. We'd have to row reduce to check, but there is at most 3 pivots. Let's think of the reason why about that. This is a 4x3 matrix, so 4 rows, 3 columns, and it's about those columns. Best case is that there are 3 pivots. Maybe when we go to row reduce, we find that it's a pivot here, a pivot here, a pivot here. But in that case, there cannot be a 4th pivot anymore. You would have to move down and right, but there are no more columns to get a pivot any longer. This is what the echelon form would look like for the most amount of pivots. There are 3 pivots, which means there cannot be a pivot in every row. There's 4 rows in total, and we cap out at 3 pivots in the most optimal situation. Usually we think of more pivots as better in this kind of context. That means part E is automatically false. The moment we just write down the matrix on paper, we can tell by visual inspection that can never happen. So we can say by theorem 4, part E is false. And so we relate that to part D. The columns of A, we defined our own A, does not span Rm. In other words, the span here is unequal to R4 in this case. Let's say it this way, span B1, B2, B3 is not equal to R4. It's impossible in this case. We would have had to have at least 4 vectors to span a 4-dimensional space R4. Kind of makes sense when you say it that way, right? But that's really getting into issues of the dimension of R4. Later on, we'll say the dimension of R4 is 4. So to span it, you will really need 4 vectors at minimum. There's a lot more we can say about that, but we're getting to there in stages. Does that make sense to folks on how to analyze this one?
Your theorem 4 doesn't have a part A.
Oh my gosh, you're right. That is a weird, funky thing that happened there. It must have been from what I copied and pasted. Let me go part A. Thanks for mentioning that. I'm not really sure how that kind of happens. There's got to be a quick way to fix this. Right click. You know, I have a good solution to this. Let's go to the one that probably looked a little bit more normal. That theorem 4. I didn't want one that has a whole bunch of stuff writing on it. It's nice to see it when it's clean sometimes. Let me see if I could just quickly edit it in real time here. Here's part A. Here's part B. Thanks for spotting that, by the way, Joel. That was crazy how I couldn't see that until someone said something. And I think that one's right. It just looks weird now. There we go. I think that looks a little bit better. Let me make sure I didn't do that again anywhere else in the notes. Okay, that looks a little bit better. And I said part E. That should have alerted to me something was funny if I'm going all the way down to E there. By theorem 4, part D is what I should have been referring to. Other comments at the moment? I'm gonna actually screenshot this one for now. Okay, let's try another kind of a quicker concept exercise like that one. Example 7. Now, imagine what we did again on the last problem in this one, but there's something else really small going on here. If you feel like you found a typo, there's no typo here. I really meant everything here, every symbol, literally as it stands. It's an important question, even though there seems to be something kind of off about it. And again, if you try to do what we did before, put this into a matrix, we'd find a pivot here, so there would be a pivot in every row. But those two vectors do not span R3. Anyone see what the problem is on this one?
They're vectors.
Exactly. Sometimes we have to really pay close attention to what's going on with the vector space itself. This is kind of a nasty problem to put on a real exam. I wouldn't try to just change one number to see if you caught a weird notation thing like that. But these sort of things are fair game on actual homework exercises. So the big concept here is, doesn't matter if there's a pivot in every row when you put this in a matrix. If the vectors came from the wrong vector space, this is automatic no every time. So we could say here, span V1, V2 is not R3, absolutely not R3, since these vectors are in R2. The span of them would span R2. There'd be a pivot in every row. We put this both into a matrix. So watch out for these kinds of things in doing homework kind of questions. They actually play a bigger role than we think. It's not just a one-up kind of trick question. This stuff becomes a bigger deal when we're dealing with subspaces in chapter 4, where we have to make sure, well, if something is a subspace of something else, it has to be a subset in the first place. And a subset means the vectors or objects you're considering actually are contained in the larger target space. Here, they're not even in R3 in the first place, they're in R2. So that one's a really fast one. Any other additional questions on that one? Okay. Well, it's been no twice on each one of these style questions. So this one is just to try to get a problem in the affirmative direction. Example 8 says, consider these three vectors. I'll call them V1, V2, V3. We're wondering, is the span of 3 equal to R3? We have to explain it. So first of all, everything looks great. There would be a pivot here, here, and here if it were a matrix, except it's not a matrix. That's just a list of columns. So let's write out just a little bit more and say it this way. Since A equals V1, V2, V3, if you started writing right here and say has a pivot in every row, I'd say that's all right, because I would say you're just visualizing this as a matrix. For the notes, let's write it out. 1, 0, 0, 2, 5, 0, 3, negative 8, 10. So let's now say, since that matrix A just defined has a pivot in every row and every column, but keep in mind theorem 4 is all about the rows, not the column. Span V1, V2, V3 is in fact R3 by theorem 4. Then we're just done at that stage. Theorem 4 is kind of nice because these questions could actually be pretty big questions. If we worked at it directly, what would we have to do to answer that and prove it? You'd have to write down an arbitrary vector B. It would look like this. B1, B2, B3. You would augment this arbitrary vector with this as a now left-hand side, the coefficient part, start row reducing and seeing if it becomes consistent in the end. Again, our author does that only once just to show how theorem 4 can be used to answer these questions really, really rapidly now. Because it spans all of R3, it also tells us so much more. For example, every matrix equation you form is always going to be consistent no matter what. Everything is solvable. Those columns are special. Every vector B in Rm can be written as a linear combination of these three columns. And of course, we just addressed that they also span. Well, that's the end of the notes in this section, folks. Any additional questions or comments about what's going on in section 1.4? Okay, kind of a weird section because we did an algebraic technique, a matrix times a vector, and then we mostly worked out stuff abstractly, kind of learning how this theorem goes. We'll be using this theorem quite a lot throughout the course, so each time we have to use it, I'll call it out in the notes so we know exactly why we're using it, what parts we're using, and that way we get to internalize it better and better. And again, it's kind of like practice. We're going for the invertible matrix theorem, which is a huge list of logically equivalent statements. So we're practicing at that theorem all along by studying this one. The next set of notes is kind of a little bit more lighter, I'd say. It doesn't have a bigger abstract theorem like this one. In fact, it's kind of some of the similar stuff we've been looking into. It's going to be solution sets of linear systems, but very specific. Can't do this because of dialog box. Oh, there we go. So here are those systems of equations we're going to solve on this one. Homogeneous system of equations. This one has a really special role in linear algebra, this concept here. Let's open this set of notes just briefly. We looked at the structure of some of these theorems that we're getting into in section 1.3. And here's the tree diagram of interesting theorems. A lot of discussions on linear combinations and spanning so far. But now we're turning over, starting in section 1.5, to talk about linear independence. Well, linear independence is not easy to define either. Maybe not as abstract as spanning, but to get into linear independence, we have to study that specific system. That's kind of curious in a certain sense. Homogeneous systems of linear equations, either as a vector equation or as the matrix equations shown, is the big key to defining linear independence. So what makes a system homogeneous? It's if the right-hand side is a zero. Zero as a vector if it's a matrix equation. If it's a list of equations like, say, this one's homogeneous just because all of the right-hand sides are zero. So that's the common feature. Your equals to is zero either as a system, all zeros, or as a matrix equation, or as a vector equation, the right-hand side is a zero vector. Other things we can look into on this one is, if A is an m by n matrix, let me see if I can blow this up to really emphasize. If A is of size m by n, so that's for the matrix A. Let me see if I can target that better so it's not too scrunched. If A is of size m by n, it tells you something immediately by that vector x. The only way this is even defined in the very first place is if x is of size n by 1. That's what allows the matrix times the vector product to be defined. But then it tells us the size of this one. There's zero vector on the right-hand side. We grab from the outer dimensions. It's of size m by 1. So that's why it says over here, 0 is the zero vector in Rm. It has to be specifically the m entries, same as the number of entries in the matrix A is another quicker way to think about that. So that's how we define a homogeneous system. And example 1 says, let A be a 5 by 3 matrix. Find one solution to the homogeneous system, Ax equals 0, and also specify the vector space that the solution X belongs to. Example 1 feels pretty abstract, but this is also another interesting definition. It says, consider the system Ax equals 0. We want one solution. Let me just double check my color coding. Okay, just want to make sure we've got the right thing. We're looking for one solution. we're talking about X. There's a guaranteed X that would solve that matrix equation. Anyone see what it would be?
Zero.
Exactly. It has to be the zero vector. I mean, that makes sense, right? If you think of an analogy, here is the scalar equation, 5x equals 0. That has a unique solution. X is the zero scalar here. Well, if you go to the land of matrix equations, this solution here may or may not be unique. And that's a fundamental question, which is going to reveal a nature about the columns, whether they're independent or not. But this always has solution, x equals the 0 vector. Let me write out this way first, just for emphasis. I guess question for us is, anyone see how many entries there has to be inside here? Is it 5 zeros or 3 zeros? It's always kind of a tricky question, right? But here's the quick hack on working through this. This is a 5x3 matrix. So that's like the m by n. This has to be of size n by 1, but that means it has to be 3 by 1, guaranteed. Otherwise, we couldn't actually do 8 times x whatsoever. So that means x equals 0, 0, 0. So it said, specify the vector space the solution belongs to. We found the solution. I just wrote out the actual entries for emphasis. Vector or specifying the vector space would just be saying in R3. R3 because our zero vector here has the 3 entries. Or you could have just said, if you prefer, x equals a 0 vector, like that would have done just fine. This is a little bit nicer for us because it reveals why it's an R3 in the first place. So that's kind of nice. A homogeneous system, you have a solution guaranteed. In fact, the solution was so easy to find, we have a name for us. This is called, this solution, x equal to the 0 vector, is called the trivial solution. Trivial, not in the sense it isn't important, but more trivial in the sense that we didn't have to do anything. It just exists there by nature. As soon as it's homogeneous, 0 is an automatic solution to this system. Our major fundamental question then is, what are the non-trivial solutions? And later on these notes, how do we actually specify them? A really big core technique is going to come up called parametric vector form, and that's something we were hinting at in sections 1, 2, and 1, 3. So we don't have a ton of time, it looks like, to really get into it, but here's the wall text that goes along with this. Homogeneous system is ax equals 0. The 0 vector is the trivial solution, and we're going for the non-trivial ones. Also, theorem 2 comes back into play here. If you have found a solution, now there's a dichotomy, not a trichotomy. Either that solution is unique, it has only the trivial solution, or there'll be infinitely many variables, and that's going to happen when there's at least one free variable. So theorem below just rewrites that key information. This will be the stuff we look into more carefully when we come back on Thursday's class. But any questions at all, folks, with how these notes start out? Okay, pacing seems to be kind of weird in the class. It looks like I'm just doing the introductions mainly to these notes, but this one's a slightly longer section, but I think it has more similar things that we've seen before. So it's a kind of a nice review section as well at the same time. But we'll call it a day here at this point. If you have any questions, I'll be happy to help out. Otherwise, have a great afternoon, folks, and I'll see you all. We'll be back right here on Thursday's class.
Mike, for what is it, the exam next week that opens on Tuesday. I was wondering if for us online people, if it's open from Tuesday to Friday or if it's only open on Tuesday.
It's open from really Monday through Friday, just to be as flexible as possible with your schedule.
Oh, okay.
And also the testing center schedule as well at the same time. Yeah, I looked into trying to make everyone come in specifically on Tuesday, but that seemed to be a pretty hit or miss thing. The testing center kind of indicated it's best to sort of leave it open. So for each one of these exams, it's going to be open Monday in case earlier is just a better deal for you, and Monday through Friday.
Oh, okay. That's all. So thank you.
Yep, have a good one.